chalk is broken.
Professor? How is the—
Shut up, nerd! I haven't finished yet. Who are you?
I am from the future, and I...
What's in the bag?
This is my newest invention, LeChalk. Wait, no, not that. LeChalk, a mechanical lead pencil. No snaps, no dust.
You know there's better chalk?
Shut up, nerd! Oh, it's beautiful.
Don't just teach the math, control the math.
This is a great opportunity because the global chalk market was valued at $71.9 billion in 2024, and it is projected to grow to $94.9 billion by 2035. The reason why we chose this is because chalk duls over time. Chalk is commonly used by professors on the blackboard, and so chalk hands become a thing where it creates chronic messes and stains professional attire, as well as transferring abrasive dust to precious electronics. Chalk dulls on one side, so thickness becomes inconsistent when you're writing, and also on top of that, when chalk shortens through the use of it, it leads to a non-ergonomic pinch grip where your hand strains during longer lecture blocks. Manual adjustment tax is also when educators must constantly pause to rotate the chalk. This leads to micro breaks in the flow of the lecture, likewise with the student engagement.
So our initial design considerations were limiting the pen OD to 7/8 of an inch, and also being able to fit a piece of chalk around 9.7 millimeters in diameter. Next was the big design consideration was selecting a spring. So we wanted to select one early because the rest of our geometry would be decided by that spring. We ended up deciding on these two springs that met all of our requirements from McMaster. The spring we ended up using was the corrosion-resistant compression spring. So our initial design consisted of 5 components. So an outer body, an inner sleeve, a chuck, a spring, and a cap. And it had an OD of around 20 millimeters. Some issues with our initial design were having the outer body be unnecessarily complex with a ratchet mechanism in order to screw everything in. It was also far too thick. We wanted to go below 20 millimeters in OD. Our chuck geometry was too narrow for the chalk to easily move, and the chuck did not hold the chalk in place as we were writing. Also, the button required far too much effort, and it didn't have a satisfying click. And finally, we had significant manufacturing issues using the resin printers during the Form 4. So in order to improve our manufacturing processes, we added holes to all of our parts to reduce cupping issues in order to get our prints validated using minimal supports and orientations that would keep our surfaces smoother. For our chuck geometry, we ended up adding little bits, little extrusions to the flowery bits at the end that would help keep the chalk in place as we wrote with it. In terms of pen assembly and thickness, we were able to combine the inner sleeve and the outer body into one part, reducing the outer diameter by 2.4 millimeters, and we also improved our threads. In order to improve pen feel and the motion of the click, we changed the internal chuck retainer geometry to be a little taller so that you would have a solid thing to hit at the end of your click. And we also added some chamfers to the end of the chalk retainer in order to have the chuck move more smoothly along the side of it. The culmination of all the design improvements that we made was our final product. Throughout the course of the project, we had the opportunity to make 3 different prototypes of our design, with this one being the final prototype. So in order to assemble it, there are 4 components inside of it. We have the cap, the chuck, and the spring, which to save time have already been put together, and the body. The chuck and spring go inside of the body like this, and the cap screws on top to these threads. In order to use it, we click down on the button and slide chalk inside, and release, and that holds the chalk inside. In order to start getting the chalk out, you click the button on the back, like so. And that's how the chalk pen works.
For the outer housing, we prioritized ergonomics, tight tolerances, and a smooth surface finish. While aluminum machining would provide a premium feel, it would also increase cost and manufacturing complexity. Instead, we used SLA printing with clear V5 resin, which allowed us to rapidly prototype intricate geometry while achieving smooth surfaces after post-processing. The transparent resin also helps showcase the internal mechanism. The chuck is one of the most critical components since it grips the chalk and transfers force from the stream mechanism. We chose SLA printing with tough 1500 resin because it allowed us to rapidly iterate designs while maintaining good strength and flexibility for repeated use. To drive the mechanism, we used a commercial off-the-shelf music wire spring. Compared to a stainless steel or 3D printed alternatives, music wire provides higher tensile strength and better fatigue resistance, ensuring consistent performance over repeated use.
The chalk! Because the only thing breaking in your classroom should be your student spirits.